My topic is on origami construction, which is essentially using paper folding or origami to construct lengths, just like using a straight edge and compass. But it turns out that if you use origami, you can actually create more things. More things are possible. So when you normally use a straight edge and compass, you have two constructions that you can do basically. There's C1, I'm calling it C1, which is the straight edge function, and C2, which is the compass function. And those do exactly what you would expect. C1 creates a line from 2 points, and C2 creates a circle around a point with a certain radius. And with these two constructions, we can get basically three intersections, which I'm calling P1, P2, and P3. P1 is an intersection between two lines. P2 is an intersection between a line and a circle, and P3 is an intersection between two circles. And with origami, we get this third construction, which I'll call C3, very creatively, which says that for 2 points, alpha and beta, which are distinct, you can reflect alpha to a line L1 and beta to a line L2, which are different from each other. And you can see how that's done in this picture. You fold it. Okay, so first off, before we get too deep into origami, we should probably get a formal idea of what it means to be constructible normally. So, using just a straight edge and compass, a number alpha is constructible if and only if you can get alpha from the rationals by taking a series of field extensions from the rationals to whatever field alpha is in, such that every step you take has degree 2. And the definition I have right here, this is like the rigorous one, and it uses field theory pretty clearly. And this green notation right here is called a tower of fields, which is important because I'm going to mention that several times when I talk about origami. Okay, so and it has to be degree 2 because when you have circles and you want to solve for intersections with circles, you'll have to take square roots, and that's what essentially it means to have degree 2. You're taking square roots of things. So let's look at an example of what you can do with origami. Suppose you start with a square sheet of paper, and you fold once right here, parallel to the bottom of the sheet. And then you fold again, equidistant from the first fold, also parallel to the bottom. Then you create an arbitrary angle theta with vertex in the lower left corner and create this fold. Now we can use C3 to take point P to line L1 and point Q to line L2 simultaneously, and that creates this fold right here. And well, the significance of this construction is, as you can see, I black boxed the fact that alpha is actually 1/3 of theta, which means we just trisect an angle using origami. The proof of this involves some pretty basic angle chasing and congruent triangles, but I don't exactly have time to present that to you. So if you want, you can try it out on your own, or you can ask me after the lecture, or whatever. But yeah, so what is it about this new construction that allows us to trisect angles? Well, a surprising fact is that it involves parabolas. So for those of you who don't know or may have forgotten, a parabola is defined to be the locus of points that are equidistant from a line, which we call the directrix, and a focus, a point, not on the line. And so in this case, we have two specific parabolas that I didn't draw in that we want to think about. But the first one is the one with focus Q and directrix L2, and the one with focus P and directrix L1. And the reason that we're looking at these two is because, actually, if you look at the parabolas, the fold that we created using C3 is actually a mutual tangent to both of these. And that is a fact that we're going to exploit. Again, I don't exactly have time to prove it to you, but if you really are curious, you can ask me after the lecture, and I can try to walk you through it pretty quickly. Okay, so let's look at an example of how this can help us do impossible things, or things that would be impossible otherwise. So consider these two parabolas. The top one has equation y equals 1/2 x squared, and the horizontal one has an equation y minus 1/2 a squared equals 2bx for some arbitrary real values of a and b. And suppose we want to find the slope of this yellow tangent line. Well, if you look at each individual parabola and the tangent point, we can use some basic calculus and to Okay, no, you know what I mean. you can pretty simply find like m with respect to the equation, and then we can solve for x1 and y1 with respect to n and to a and b. And similarly for the second one, we can find x2 and y2 in terms of n. Which means that if we use the slope formula, we can create a system of equations that eventually get us to this magic cubic. Which means that if we use our new construction C3 on this graph, we can actually construct the solution to a cubic equation. And this is even cooler because if you can get a cubic in this form, you can actually solve any cubic, assuming you already know the coefficients. And the reason for this is pretty cool. So suppose that you have a cubic x cubed plus ax squared plus bx plus c equals 0. What happens if you substitute y equal if you substitute x with y minus a over 3? Well, there are only two squared terms that we're going to need to worry about. The one in the x squared and the one x cubed and the one in the ax squared. The x cubed term here will be 3 times negative a over 3 times x squared, which is negative ax squared. And this one, oh, y squared, sorry, my bad. And this one will be ay squared, which means that these two will cancel out, which means that for any cubic, you can actually transform it to get rid of the squared term. And that also means that we can pretty much solve any cubic if we transform it first. Another cool thing about origami is that you can actually make straight edge and compass constructions obsolete. You can use C1 and C2 constructions without a straight edge or compass. And I will show you how to do that really quickly right here. Suppose you want to draw a straight line between these 2 points. Well, this is pretty simple. You can just fold the edge of the paper to these points and trace it. And, well, it should be a line. Suppose that you want to have a circle with this center and this radius. Well, what really matters about the circle are the intersections it makes with other things. So we don't actually have to draw the circle, we just have to be able to draw the intersections. So suppose we have this line, and we want to find the intersection of this imaginary circle onto this line. Well, we can create a reflection axis through the center such that this goes onto the line. And that's pretty easy to do if you have paper, you can just fold it that way. So that's how you can replace the straight edge and compass using just origami. Okay, so now that we know what origami can do, we should probably formalize what it means for a number to be constructible using origami. And we'll say a number alpha is an origami number if you can have a finite series of constructions using C1, C2, and C3 and our intersections P1, P2, and P3, such that if you start with points 0 and 1, you can eventually make it alpha. Okay, so now I'm going to propose a characterization theorem of the origami numbers, which will look very similar to the constructibility one I mentioned earlier, with one small difference. And again, it uses the Tower Fields notation. So let O, a subset of R, be the set of all origami numbers. Then alpha is an element of O if and only if you can get alpha from the rationals by extending through a series of field extensions where each step takes degree 2 or 3, which you can see is a more powerful version of the previous one. And we can prove this using a bijection since there's an if and only if. So suppose that we assume that alpha is in a certain tower of fields where each extension is a degree 2 or 3 extension. And we want to prove it's an origami number, and we're going to use induction. So for the n equals 0 case, alpha is just in f0, which is the same as the rationals. And we already know that we can construct rational numbers using only our straight edge and compass constructions, so that's an easy case. And we can assume that the n minus 1 case is true, because that's how you do induction. And we want to show that if alpha is in Fn, and the degree of Fn over Fn minus 1 is 2 or 3, then alpha is an origami number. Another way of saying this is alpha is a root of a polynomial p of x with coefficients in the origami numbers, where the degree of p is either 2 or 3. And if we want to solve a quadratic or cubic equation, given the coefficients, Well, we know we can do quadratics using normal construction. And we have just showed rigorously that we can also solve any cubic. So that side is done. We're good. Now we should do the other direction. Suppose that alpha is an origami number, and we want to show that we can construct a tower of fields such that each field extension is either degree 2 or 3. Okay, so in each step of our construction, we're going to either use P1, P2, or P3, our intersections, to eventually get to alpha. So we can look at each case and show that in every case we have to get into the tower of fields. So suppose we have P1, which is an intersection between two lines. Well, there are two different ways we can make lines. We can either use normal straight edge construction, C1, or we can have our new origami construction, C3. Well, if the lines are C1, it's pretty easy because if you start with a line with rational coefficients and you intersect another line with rational coefficients, your intersection will also be rational. And it's the same for more complicated cases. So that's good. But if one of the lines is in C3, then that means our intersection is going to have some kind of cubic term in it somewhere. But that's good because we know that the solutions to cubics are a degree 3 extension. So this is also good. Now suppose that we have a P2 intersection. We have an analogous case here. Suppose the line is C1. Then we have a normal line and a circle which has square terms in it. And if we want to solve for the intersections, we will have to take square roots. But that's